Why quantum computers can't be hacked. Quantum computers are revolutionizing the way we think about computing, offering extraordinary speed and power that far surpass classical computers. But beyond their computational advantages, there's growing excitement and concern about their potential impact on cybersecurity. Interestingly, while quantum computers could eventually break many current encryption systems, they also offer unique properties that make them incredibly difficult to hack. Let's explore why. At the heart of a quantum computer is the qubit, a quantum version of the classical bit. Unlike classical bits that can only be 0 or 1, qubits can exist in superposition, meaning they can be both 0 and 1 at the same time. This allows quantum computers to perform multiple calculations simultaneously. But superposition alone isn't the reason they're secure. The real key to their security lies in another quantum principle called entanglement. Entanglement means two or more qubits become linked, such that the state of one instantly affects the state of the other, no matter how far apart they are. This enables a form of communication and correlation that cannot be intercepted or tampered with without being detected. If a hacker tries to eavesdrop or interact with entangled qubits, the quantum state collapses. This collapse immediately signals that the system has been disturbed, alerting users to a potential intrusion. This concept is used in quantum key distribution, QKD, a way to securely transmit cryptographic keys with guaranteed detection of any hacking attempt. Another major feature is the no-cloning theorem in quantum mechanics. In classical computing, data can be copied easily, but in quantum systems, it's physically impossible to create an exact copy of an unknown quantum state. This means a hacker cannot make a duplicate of a qubit to study it or attempt a stealthy attack. Any effort to intercept or replicate the data automatically alters the original state, thus triggering detection. This makes eavesdropping practically impossible without being noticed. Moreover, quantum communication networks are built using quantum encryption methods that are fundamentally unbreakable under known physics. Traditional encryption relies on mathematical problems like factoring large numbers or solving discrete logarithms, tasks that quantum computers will eventually crack. But quantum encryption doesn't depend on math problems. It relies on the laws of physics, particularly the quantum properties of light particles, photons. This makes hacking a quantum encrypted message as impossible as violating the fundamental rules of nature. Also, in quantum systems, measurement itself is a form of interference. You can't measure a quantum system without disturbing it. In other words, any attempt to spy on or extract information from a quantum system automatically changes it, thereby making such actions detectable. This provides a level of security that no classical system can offer. But it's important to understand that while quantum computers themselves are secure, the systems surrounding them, such as the classical components like user interfaces, servers, and network connections, could still be vulnerable. Hackers may still exploit human error, poorly written code, or traditional backdoors. So, quantum security is only as strong as the weakest link in the entire system. That's why researchers are also working on post-quantum cryptography, which involves developing new algorithms that are secure even against quantum attacks. In short, quantum computers are hard to hack not because of any single feature, but because of the fundamental principles of quantum physics: superposition, entanglement, the no-cloning theorem, and measurement disturbance. These laws make unauthorized access extremely difficult. Any attempt to tamper with a quantum system leaves a trail. Unlike traditional security methods that rely on complexity and obscurity, quantum security is based on transparency and physical law. You don't just hope the hacker can't get in. You'll know if they try. In the coming years, as quantum technology becomes more mainstream, industries like finance, healthcare, defense, and national infrastructure are likely to adopt quantum-secure communication channels. Governments and companies are already investing heavily in quantum-safe technologies, not only to guard against future quantum attacks, but also to harness the unparalleled safety quantum mechanics provides. To conclude, quantum computers can't be hacked in the conventional sense because their core operations are governed by the unbreakable rules of quantum physics. They represent a future where information security may be more about physics than software, a shift that could fundamentally change the cybersecurity landscape forever. Like and subscribe.